Welcome to this coding problem walkthrough. In this video, we'll explore the problem of calculating the number of unique binary search trees that can be formed with a given number of nodes. This is a fundamental problem that tests your understanding of recursion, dynamic programming, and binary tree properties. Let's dive into the details and solve it step by step. In this problem, we are tasked with finding the number of structurally unique binary search trees, or BSTs, that can be formed using a given number of nodes. Specifically, if we have an integer n, which represents the number of nodes, we want to determine how many distinct BSTs can be constructed using the values from 1 to n. For example, if n equals 3, there are 5 unique BST configurations. The input for this problem is a single integer n, where n can range from 1 to 19. The output is also a single integer, representing the count of these unique BST structures. This means we need to account for all possible arrangements of the nodes that satisfy the properties of a BST. To understand the output for n equals 3, let's break down the different configurations of the BSTs. First, when the root node is 1, there is no left subtree because there are no smaller values, and the right subtree contains a BST where 2 is the root and 3 is its right child. Next, when the root node is 2, the left subtree is a BST where 1 is the root, and the right subtree is a BST with 3 as the root. Finally, when the root node is 3, the left subtree is a BST where 2 is the root with 1 as its left child, and there is no right subtree because there are no larger values. These 3 root configurations together give a total of 5 valid BSTs. Now, for n equals 1, there is only one possible BST structure, which is a single node with no left or right subtrees. With n equals 1, the output is 1 because there is only one way to structure a BST with a single node. This node serves as the root, and there are no left or right subtrees. Moving forward, it's important to note some constraints. The value of n will always fall between 1 and 19, and the result will fit within a 32-bit signed integer. Additionally, the nodes are distinct and numbered sequentially from 1 to n. This problem also has a connection to the Catalan number sequence, which is a mathematical concept that arises in problems involving unique structures like BSTs. A binary search tree, by definition, ensures that all nodes in the left subtree have values smaller than the root, and all nodes in the right subtree have values greater than the root. This property is what makes the structure unique for each arrangement. To solve this problem, we can use either dynamic programming or recursion with memoization. Both of these techniques allow us to efficiently compute the number of unique BSTs by leveraging the relationships between smaller subproblems. Dynamic programming involves storing results for smaller values of n and building up to the desired result, while recursion with memoization avoids redundant computations by caching the results of previously solved subproblems. Both approaches exploit the recursive nature of the problem, where the number of unique BSTs for n nodes can be derived from the counts of BSTs for smaller numbers of nodes. To tackle the problem of finding the number of unique binary search trees for a given number of nodes, one approach we could consider is brute force. The idea here is to generate all possible binary trees with n nodes and check if each one satisfies the binary search tree property. Remember, a binary search tree is valid when, for every node, all nodes in the left subtree are smaller, and all nodes in the right subtree are larger. To implement this, we use recursion. For each number, we treat it as the root, then recursively build all possible left and right subtrees. However, the drawback is that this approach is computationally expensive. Generating all possible trees involves exploring every combination of nodes, leading to an exponential time complexity, specifically around 2 to the power of n, or worse. While the concept is straightforward, this method quickly becomes infeasible even for relatively small values of n due to the sheer number of combinations involved. To address the inefficiency of the brute force approach, we can turn to dynamic programming. This optimized method leverages the mathematical properties of the Catalan number to count unique binary search trees without explicitly generating them. The key insight is that the number of unique BSTs for n nodes can be determined recursively. For each potential root, the left subtree will contain i1 nodes, and the right subtree will have ni nodes. The total number of unique BSTs is the sum of all combinations of left and right subtrees across all root choices. Mathematically, the formula is dp n equals sum dp I1 * dp n I for all values of I from 1 to n. With base cases defined as dp 0 equals 1 for an empty tree and dp 1 equals 1 for a single node tree, we can iteratively compute the values for larger n using an array dp. This method improves efficiency significantly. The time complexity is O n squared due to nested loops, while the space complexity is O n for the dp array. Unlike brute force, dynamic programming avoids the need to generate all trees explicitly, making it suitable for larger values of n. Additionally, we can turn to the mathematical approach using Catalan numbers, where the nth Catalan number, Cn, directly gives the number of unique BSTs. This is computed as Cn equals 2n / n plus 1 * n. While this approach is faster, with complexity around O, n, or faster with pre-computed values, it is less intuitive and requires familiarity with combinatorics. Given the available methods, the dynamic programming approach emerges as the preferred strategy. While the mathematical approach is undeniably efficient, dynamic programming offers a more intuitive path to understanding the problem, as the recurrence clearly breaks down the relationship between subproblems. Additionally, it avoids potential numerical precision issues that can arise from computing large factorials in the Catalan formula. A key insight here is recognizing that the problem revolves around counting combinations of left and right subtrees for different root nodes. This recursive relationship becomes the foundation for solving the problem systematically. Comparing the methods, the brute force approach, while conceptually useful, is computationally prohibitive. The mathematical approach, though fast, requires a solid grasp of combinatorics, making it less accessible. In contrast, dynamic programming strikes a balance between clarity and efficiency. This makes it the most practical solution, especially given the problem constraints of 1 equals n equals 19. By implementing this approach, we achieve a scalable solution that is both easy to understand and efficient in practice. In this problem, our goal is to generate all structurally unique binary search trees, or BSTs, that can be formed using n distinct nodes. A binary search tree follows a specific property: for every node in the tree, all values in the left subtree must be smaller, and all values in the right subtree must be larger. This ensures that the tree remains ordered. The challenge here is to efficiently generate all these unique trees without creating duplicates or invalid structures. To tackle this, we start by understanding the recursive nature of the problem. A BST with n nodes can be built by choosing a value I ranging from 1 to n as the root of the tree. Then, we divide the remaining nodes into two groups: those smaller than I form the left subtree, and those larger than I form the right subtree. We repeat this process recursively to construct all possible left and right subtrees, ensuring that we cover every valid combination of trees for a given root value. To break this down further, we start with some base cases. If there are no nodes, which means n equals 0, the only valid tree is an empty tree, represented as null. If there is just one node, n equals 1, and the only valid tree is a single node with no children. From here, we build larger trees using recursive construction. For every value I in the range from 1 to n, we treat I as the root of the tree. Then, we recursively generate all possible left subtrees using the values from 1 to I1 and all possible right subtrees using the values from I plus 1 to n. Once we have all combinations of left and right subtrees, we connect them to the root node I to form complete trees. Each of these constructed trees is added to our list of results. Finally, after iterating through all possible root values, we return the complete list of unique BSTs. There are several important insights that simplify this problem. First, the recursive nature of the problem allows us to break it into smaller subproblems, generating BSTs for subsets of nodes. This makes recursion a natural fit. However, recursion alone can lead to redundant computations. To optimize, we use dynamic programming with memoization, storing results for specific ranges of nodes so that we don't recompute them. Another key insight is that the total number of unique BSTs corresponds to the Catalan number, a well-known sequence in combinatorics. This reveals the combinatorial complexity of the problem. Additionally, the symmetry in tree construction can help us reduce redundant calculations by identifying repeated patterns. To implement the algorithm, we primarily rely on two data structures: a list to store all possible BSTs for a given range, where each tree node has a value, a left child, and a right child, and a memoization table, which maps a range represented as a tuple, start, end, to the list of BSTs for that range. Now let's analyze the complexity of this algorithm. The time complexity is proportional to the Catalan number, denoted as C_n, because constructing each BST involves combining all possible left and right subtrees. Since C_n grows exponentially, the time complexity reflects this growth. For space complexity, we need to account for both memoization and the storage of all constructed trees. Each tree node is stored exactly once, so the total space usage is also proportional to C_n. For a concrete example, consider the case where n equals 3. If we pick 1 as the root, the left subtree is empty, and the right subtree consists of trees formed from the values 2 and 3. If we pick 2 as the root, the left subtree is formed from the value 1, and the right subtree is formed from the value 3. Finally, if we pick 3 as the root, the left subtree consists of trees formed from the values 1 and 2, and the right subtree is empty. This systematic exploration ensures that all valid BSTs are generated. Once all combinations of left and right subtrees have been explored for every possible root value, we combine the results. This gives us a comprehensive list of all structurally unique binary search trees that can be formed within nodes. The algorithm ensures that we efficiently account for every valid structure while avoiding duplicates, providing a complete solution to the problem. The provided Python implementation solves the problem of counting unique binary search trees, BSTs, for a given number of nodes, n. The problem is addressed using dynamic programming, DP, where the number of unique BSTs for a specific number of nodes is calculated iteratively based on smaller subproblems. 1. Initialization. We start by creating an array DP of size n+1, where DP, I, represents the number of unique BSTs that can be formed with I nodes. We initialize DP, 0, and DP, 1, to 1 because there's exactly one way to form a BST with 0 nodes, an empty tree, and 1 node. 2. Iterative calculation. For each number of nodes from 2 to n, we compute DP, nodes, by considering every possible route from 1 to nodes. For a given root, the number of nodes in the left subtree is root 1. The number of nodes in the right subtree is nodes root. The total number of BSTs with this root is the product of the number of BSTs possible in the left and right subtrees, DP, left, *DP, right. 3. Final result. After iterating through all possible numbers of nodes and roots, the value of DP, n, contains the total number of unique BSTs for n nodes. This approach is efficient, with a time complexity of O(n²) due to the nested loops, and a space complexity of O(n) for storing the DP array. The algorithm avoids redundant calculations by leveraging previously computed results, making it well-suited for this combinatorial problem. This is the Java implementation for LeetCode problem number 96, Unique Binary Search Trees. It mirrors the Python solution by using dynamic programming to calculate the number of unique BSTs. Key differences include the use of Java's type declarations and array syntax. The DP array is used to store intermediate results, and nested loops calculate possible trees for every node count. This approach ensures clarity and efficiency, with the same logic as the Python equivalent. To calculate the number of unique binary search trees for n equals 3, we start by initializing a dynamic programming array, DP, with n+1 elements. Initially, it's set to 0, 0, 0, 0. We define base cases where DP, 0, equals 1 and DP, 1, equals 1, since there's exactly one way to arrange either 0 nodes or 1 node into a BST. After setting up the base cases, the array becomes 1, 1, 0, 0. Next, we compute DP, 2, where we evaluate all possibilities of assigning the root node. For nodes equals 2, if node 1 is the root, the left subtree has 0 nodes and the right subtree has 1 node, contributing DP, 0, *DP, 1, equals 1. If node 2 is the root, the left subtree has 1 node and the right subtree has 0 nodes, contributing another DP, 1, *DP, 0, equals 1. Adding these values gives DP, 2, equals 1 plus 1 equals 2. The updated DP array is now 1, 1, 2, 0. Now, we calculate DP, 3, for n equals 3. Again, we consider each node as the root and compute the number of unique BSTs for each configuration. If node 1 is the root, the left subtree has 0 nodes and the right subtree has 2 nodes, contributing DP, 0, *DP, 2, is equal to 1 times 2 equals 2. If node 2 is the root, the left subtree has one node and the right subtree also has one node, contributing dp1 asterisk dp1 is equal to 1 times 1 equals 1. Finally, if node 3 is the root, the left subtree has two nodes and the right subtree has 0 nodes, contributing dp2 asterisk dp0 is equal to 2 times 1 equals 2. Adding these values together gives dp3 equals 2 plus 1 plus 2 equals 5. The updated dp array becomes 1, 1, 2, 5. For n equals 3, the total number of unique BSTs is dp, 3, equals 5. Moving to n equals 4, we start by initializing a new dp array as 0, 0, 0, 0, 0, and setting the same base cases, dp 0 equals 1 and dp 1 equals 1. After initialization, the array becomes 1, 1, 0, 0, 0. The result for dp 2 remains 2, as explained earlier. The result for dp 3 is also carried over, which we know is 5. Now, we calculate dp 4 for n equals 4. Considering each node as the root, if node 1 is the root, the left subtree has 0 nodes and the right subtree has 3 nodes, contributing dp 0 asterisk dp 3 is equal to 1 times 5 equals 5. If node 2 is the root, the left subtree has one node and the right subtree has 2 nodes, contributing dp1 asterisk dp2 is equal to 1 times 2 equals 2. If node 3 is the root, the left subtree has 2 nodes and the right subtree has 1 node, contributing dp2 asterisk dp1 is equal to 2 times 1 equals 2. Finally, if node 4 is the root, the left subtree has 3 nodes and the right subtree has 0 nodes, contributing dp3 asterisk dp0 is equal to 5 times 1 equals 5. Adding these values gives dp4 equals 5 plus 2 plus 2 plus 5 equals 14. The updated dp array becomes 1, 1, 2, 5, 14. For n equals 4, the total number of unique BSTs is dp4 equals 14. Finally, for the edge case where n equals 1, we start with a dp array initialized as 0, 0. We set the base cases, dp0 equals 1 and dp1 equals 1. The array becomes 1, 1 after initialization. Since there's only one node, no further calculations are needed. The result is directly dp1 equals 1, meaning there's exactly one unique BST for n equals 1. To analyze the time complexity of our dynamic programming solution, let's break it down step by step. First, we have the outer loop, which iterates from 2 to n, inclusive. This gives us n iterations in total. Inside the outer loop, we have an inner loop that runs from 1 to the value of the current nodes. For a specific nodes equals k, this means the inner loop executes k iterations. Now, within each iteration of the inner loop, the computation dp nodes plus equals dp left asterisk dp right occurs, and this operation is constant time, or O1. So, to calculate the total number of iterations across both loops, we sum the first n integers, 1 plus 2 plus 3, and so on, up to n. This summation formula simplifies to n asterisk, n plus 1, slash 2, which is n squared. Therefore, the overall time complexity of the algorithm is governed by these nested loops, making it n squared. Now, let's discuss the space complexity of the solution. The primary contributor to space usage here is the dynamic programming array, or DP. This array is initialized with n plus 1 elements, where n is the input, leading to n space. Apart from the DP array, there are no recursive calls or additional data structures used, meaning the auxiliary space is 1. As a result, the overall space complexity is dominated by the DP array, which gives us n. When we compare this to a brute force approach, the differences are striking. A naive solution would involve recursively generating all possible binary search trees for n nodes, validating each one, and counting the unique results. This brute force method has a time complexity of 4 to the power of n/sqrt, n, tied to the computation of the nth Catalan number, and requires n space for the recursion stack. The dynamic programming approach offers a huge improvement over brute force. By leveraging the Catalan number formula and storing intermediate results in the DP array, the time complexity is reduced to n squared, while the space complexity remains n. To further explain the time complexity mathematically, consider the total time spent in the nested loops. This is proportional to the summation of the first n integers, 1 plus 2 plus 3, and so on, up to n. Using the formula for this summation, we get t, n, equals n asterisk, n plus 1, slash 2, which is approximately n squared slash 2. Disregarding the constant factor, this simplifies to O, n squared. Compared to the exponential nature of the brute force approach, the dynamic programming method is far more efficient and optimal for solving this problem. When solving the unique binary search trees problem, there are several common mistakes to be mindful of. First, it's easy to forget the fundamental BST property during recursive calls. Remember, all nodes in the left subtree must be less than the root, and all nodes in the right subtree must be greater. Violating this rule leads to incorrect solutions because the trees generated won't be valid BSTs. Another frequent issue is inefficiently recomputing the same subtree structures over and over. Without memoization, this redundant computation can drastically increase the time complexity of your solution. Additionally, some confuse binary trees with binary search trees, mistakenly generating all binary trees without checking if they meet the BST constraints. This results in invalid trees being included in the result. Finally, incorrect base case handling is another pitfall. Failing to properly handle base cases, like when there's an empty tree or a single node tree, can lead to runtime errors or inaccurate results, especially for smaller input sizes. Another mistake to watch out for is overlooking symmetry in BST construction. Certain subtree combinations are symmetric and can be reused, but building each subtree independently without recognizing this symmetry leads to redundant computations and reduces the efficiency of the solution. Now, from an interview perspective, this problem is a classic example of the Catalan number sequence. Understanding the recurrence relation for Catalan numbers, which is given by the formula C, n, equals the sum of C, I, times C, n minus I minus 1, for all valid I, can simplify and optimize your solution significantly. To avoid inefficiency, you should emphasize using memoization or dynamic programming to store results of subproblems. While recursion is often the most intuitive approach for tree-related problems, interviewers might challenge you to provide an iterative or bottom-up dynamic programming solution as a follow-up. You should also be prepared to discuss edge cases, such as when n equals 0, representing an empty tree, or n equals 1, representing a single-node tree. Lastly, it's important to understand the scalability of your approach, particularly the time complexity, which is O, n times C, n, where C, n, is the nth Catalan number, as well as the space complexity implications of your solution. This problem is closely related to several other LeetCode problems, which makes it a great opportunity to explore how these concepts connect. For instance, in LeetCode 95, Unique Binary Search Trees 2, you generate all structurally unique BSTs for n nodes, a natural extension of this problem. LeetCode 96, the problem we're discussing, focuses on counting the number of unique BSTs for n nodes, which directly relates to the Catalan number sequence. Then there's LeetCode 108, Convert Sorted Array to Binary Search Tree, which involves constructing a height-balanced BST from a sorted array. While this problem is more about balancing, it still connects to BST construction principles. Lastly, in LeetCode 894, All Possible Full Binary Trees, you generate all full binary trees, which is similar in spirit but focuses on a different constraint, namely, that every node has either 0 or 2 children. Exploring these related problems can deepen your understanding of tree structures and their variations. There are also alternative approaches to solving the unique binary search trees problem, each with its own trade-offs. One common method is recursive backtracking. Here, for each value of I from 1 to n, you treat I as the root, recursively generate all possible left and right subtrees, and then combine them. This approach is intuitive and straightforward to implement, but it can be memory-intensive if you don't incorporate memoization. Another option is using dynamic programming in a bottom-up fashion. In this approach, you maintain an array where each entry stores all unique BSTs for a given number of nodes. You build solutions iteratively from smaller subproblems, which is more space-efficient than recursion but can feel less intuitive. Finally, there's the combinatorics approach, where you directly compute the number of unique BSTs using the Catalan number formula without generating the actual trees. While this is highly efficient for counting, it doesn't provide the tree structures themselves, making it unsuitable if the problem requires generating the trees. Choosing the right approach depends on the problem requirements and the constraints you're working with. Thank you for watching. We reviewed the problem, broke it down into manageable steps, and highlighted the importance of dynamic programming and the Catalan number sequence. Remember, consistent practice is key to mastering these concepts. If you enjoyed this walkthrough, please like, share, and subscribe to our channel for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!